Hey there. Um, Today I'm going to talk about three different population growth models. These are the models in chapters 5, 6, and 7 of the book. I've decided to put them all together so that we can just see the big picture instead of looking at each one individually. All right, so the three different models are the constant growth model, the constant growth model, the proportional growth model, and the quadratic growth model. And we already saw the constant growth model. Let's write down what do we say. So in the constant growth model, every year the population grows by the same amount. Okay, so for each of these models, I'm going to create three different pictures. All right, so the three different, for each of these models, I'm going to create two different pictures. Um, the first one is the current population, and then the change in population. So for each of these, we're going to figure out what does the change in population look like as a function of the current population. All right, so when we talk about constant growth, then what that means is that the change in population is a constant function, or it doesn't depend on what the current population is. It says if we have 10 people in the population and we grow, if the number of people who we're adding to the population is 100 every year, it doesn't matter whether we have 1,000 people to go from 1,000 to 1,100, or to have 1 million to go from 1,000,000 to 1,100,000. So this line right here about being a horizontal line is saying that no matter what the current population is, the change in the population for the next year is going to be the same. All right. So this constant growth is this green picture. So what does that translate into in terms of the population over time? So this other picture is the population over time. So whatever our first value of the population is, the next year we add the same amount. We add this constant amount. Excuse me, we add the second amount. We add the same amount each year. Each year we're adding the same amount. And so this population over time, the population graph as a function of time is linear. All right, so I'm going to try to be very careful about talking about constant growth versus the population graph being a linear graph, because it's really easy to slip into saying this is a linear growth model. No, this is a constant growth model where the population grows linearly over time. All right, and so if we're writing down a formula for what the population is each year, well, this is what we had last time, which is that the annual growth is equal to the change in the population over the change in time. And then for that we have that the population at time 1951 is equal to the population at time 1950 plus this annual growth. Similarly, population at time 1952 is equal to the population at 1951 plus this annual growth. We'll put one more just because why not? The population at 1953 is equal to the population at 1952 plus this annual growth. I find it really helpful to write this out year by year because it's giving us a feel for what we want the computer to do when we simulate it. We want to write down what's the formula for year t plus 1 as a function of year t. And so here we're really starting to see this is what the function should look like. All right, proportional growth. So for proportional growth, then the rule here is that every year the amount of births and the amount of deaths is proportional to the population size. So in other words, if maybe we have 1% of the population, if we have a population of size 1,000 and we have 10 people born, then if we change the population to 10,000, we might expect 10 times as many, so 100 people to be born. So this is saying that as a function here of what is the change in population based on the current population, what that's saying is that it's a line through the origin. So there's some slope here that says that the number of births and the number of deaths is a function that's proportional to the current population size. So how does that impact the graph, the population graph? So let's think about this. If we have the population at a certain value, then what we're saying is we're taking the current population and there's some amount that's being born relative to that, and there's some amount that's dying relative to that. And so whatever the value is, it takes the value at time t and it multiplies by a constant to get to time t plus 1. So we multiply by 1.01, multiply by 1.01 again, multiply by 1.01 again, multiply by 1.10 again. So if you keep doing this, instead of being a linear, the population graph being linear, instead the population graph as a function of time is exponential. So if we start off with a graph and the population has a proportional growth model, then we would expect the population to grow exponentially. So if we let b be equal to the birth rate and d be equal to the death rate, then what's the population at time 1951? Well, it's going to be equal to the population at 1950 plus however much it grew. So how much did it grow? So I'm going to take a little bit of space here and then I'll reclaim it later. So population 1950, well, we add the number of births. Well, the number of births is equal to b times the population at 1950. Right? We take the current number of people and multiply by this factor of the birth rate. And then we have to subtract off the number of people who die. And that again is also a factor, a multiplicative factor of the current population. So if you look at this expression, then what we're seeing is that we have the same factor appearing in each of these three terms. So if we factor it out, we get the population at 1951 is equal to the population at time 1950 times 1 plus b minus d. So that's a number like 1.01 or 1.02, something like that, if we're thinking human scale. But if you're thinking about something that doubles, then that's going to be a number like 2. So we're seeing that the population at 1951 is equal to the population in 1950 times 1 plus b minus d, or the population at 1952 is equal to the population at 1951, where we have this same value for how many people are being, what proportion of the population is being born and dying. And then the population at 1953. So why don't we, instead of writing each year, let's write the general case. So the population at time t plus 1 is going to be equal to the population at time t times 1 plus b minus d. And here it was the population at time t plus 1 is equal to the population at time t plus the annual growth. All right, like I said, I'm going to reclaim my space here. And draw this line again. And we're going to talk about one last model, the quadratic growth model. So in the quadratic growth model, we have a different rule. And I think I'm going to move myself over to the other side of this screen. Whoa! Okay, over here. All right, so the quadratic growth model, the rule here is that every year the amount of net growth is a quadratic function of the population, of the current population of the population. All right, let me draw this, and then let's talk about it. Okay, so I'm going to draw a parabola here. And let's talk about the different ranges of this parabola. All right, so we've got this part of the curve. So we've got the green part of the curve, we've got the yellow part of the curve, and we've got this red part of the curve. All right, and so what does that correspond to? So this blue part of the curve, this green part of the curve, you can see here that kind of looks like the proportional growth. That kind of looks like this proportional growth type of structure. There's no limits on maybe the vegetation or the space that's available. And so in this range, we would say that the population is growing exponentially. All right. Whereas as the population grows and grows, then you might get to this place up here, this yellow part, and in that yellow part you might think, oh, we're starting to mature as a population. We're getting to a place where we're going to kind of grow linearly over time because we're starting to get into some maybe resource allocation, resource issues. So in this yellow range, then the population grows almost linearly. Okay, and here I'm getting myself into trouble again, right? I don't actually mean the population grows exponentially. I'm talking about the population, the population graph looks like an exponential graph. In that second region, the population graph looks like a linear graph. And then in this final range here, in this red range, well, as the population grows and grows and grows, it has to slow down. It has to slow and slow and slow. So the rate of change of the population is slowing down. So in this range, the population increases slower and slower up to a limit. Okay, so if we're going to draw the graph of what the population looks like over time, at the beginning part, the graph is going to increase exponentially, and then the graph is going to level off and grow linearly, and then it's going to grow slower up until this point right here. And let me change the color again. So this point right here, this population, is called the carrying capacity of the of of the population. So this is the carrying capacity of the system, is the limit at which the population can't grow anymore. Okay, and so this kind of curve is called a logistic curve. So this, I didn't put here time, the population over time. This is called a logistic curve. And it comes from this quadratic growth model. And so now what we're going to do is we're going to write down just like we have on these other two, we're going to write down what the 1 year to the next looks like. So what it looks like is the population at 1951, it's going to be equal to the population at 1950 plus the net growth. All right, and what we said the net growth looks like is it looks like some constant. So I'm going to actually make a little bit more space for us here. So the population in 1951 is population 1950 plus the net growth, which we said is some constant alpha times the population at 1950 plus some constant, here this is beta, times the population at 1950 squared. Okay, and so we've started off, this is what our formula is going to look like in general. So what do we have here? We have the population at time t plus 1 is going to be equal to the population at time t plus this net growth, which is alpha times the population at time t plus beta times the population at time t squared. All right, so there's one thing that we're going to need when we put this into the computer. Might as well say it now. which is if we want to take something and square it, you do not use, right, where you may be used to writing something like this, pop of t squared, caret 2. In Python, that's not the way to square something. In Python, the way to square something is you write pop of t star star 2. That's how you're going to do that. All right. We'll see that in the next video when we take all these things that we just learned about and we then put them into practice. All right, see you shortly.